So today we're going to review limits. The first thing I'll do is read the definition. If the limit as x approaches c from the left of f of x is a value, and the limit as x approaches c from the right of f of x is a value, then the limit as x goes to c of f of x exists, and that value will be the same number as the left and right limit. So that's what that L stands for. And so we remember that when we look at a graph, you approach from the left, you approach from the right, and essentially your fingers, as you trace the graphs, they have to meet at a singular point. And the point can be a whole removable discontinuity, or it can be a physical point that exists. So the point doesn't have to exist for the limit to exist. Okay, so let's write that here. Point does not have to exist for a limit to exist. All right, so I have two problems that I want to deal with underneath. The first one here on the left, we're going to look for the limit as x approaches 2. And so first we're going to do it from the left. So if I trace my graph in red from the left side, I'll end up approaching this removable discontinuity, and that value is at 3. Then we're going to trace from the right in purple. And that also approaches the removable discontinuity at 3. And because we have the left and the right limit values to be exactly the same, therefore the limit as x goes to 2 of f of x, it exists and it will be the exact same value. Notice that the point at 2, 3 is a removable discontinuity. It actually does not exist on the graph. Okay? Let's look at the one to the right. We're going to do the same thing. In red, I'm going to do the limit as x approaches -1 from the left side. And that approaches a value of 1, 2, 3, 4. Then in purple, I'm going to do the limit as x approaches -1 from the right side. In purple. And that goes to a value of, we'll consider that 2. It's a little bit off, but that was just because I drew my lines a little bit off. So if you notice, and we'll do this in orange, the left limit and the right limit are not equal. So the limit as x goes to -1 of f of x does not exist. You can put does not exist, or you can put undefined. I tend to always put does not exist. Okay, so now we're going to try some limit problems that I know the class was struggling with. We're going to start off by looking at the limit to a value. And I did want to put some of the more difficult ones here. We know that when you do a limit to an actual value, the first thing you try to do is substitute. And if it doesn't work, meaning if you get undefined as an answer, then you try to factor, or you may have to simplify. Okay, so what I'm going to do is actually show you the graph of both of these, and that will actually help you figure out what the limits are. And I'm actually going to do, for the number 1, we're going to do a limit as x approaches 4 from the left, and we're also going to do a limit as x approaches 4 from the right. And obviously it's because we're trying to find the limit at x equal to 4. So first thing I'm going to do is just put in some lines to make my graph. And then let's put some tick marks. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4. 1, 2, 3. And what we're going to do is at 4, we know that there's something going on. And we know it's undefined because if you put 4 in for x, you're going to get 0 over 0. So the next thing I'm going to try is I'm going to put in 1, 2, 3, 4. I'm going to put in 5. So that would be 1 divided by 1. So that gives me 1. 6 would give me 1. 7 would give me 1. And I'm just substituting in values. Then I'm going to try 3. If I substitute in 3, the top becomes positive 1, but the denominator, you actually get negative 1. So positive 1 divided by negative 1. And if you keep doing these values, you get this. And if I did 4.1, that would end up being 4.1 divided by 1. If I did 3.9, that would be 3.9 divided by negative 3. So 3.9, sorry, that would be 0.1 divided by negative 0.1. You end up with a graph that looks like this. And like I said, the easiest thing is to attempt to draw the graph using a table. And so you can see by looking at the graph, the limit as x approaches 4 from the left side goes to negative 1. But as x approaches 4 from the right side, we approach a value of 1. So the limit as x approaches 4 of f of x does not exist. But if I asked you a limit anywhere else, even if it was 4.1, the limit would exist. Let's look at the one to the right because most people just answer the same exact answers for these. For this graph, and we're going to do the same thing. We're going to do a limit at 4. So I'm going to put in axes again. We're going to create the graph. Okay, so looking at this guy, let me put this back in black. 1, 2, 3, 4, 5, 6, 7. Okay, so at 4, again, we know it's going to be undefined. But if I put 5 in here, so I'm actually going to show the table right here. If I put 5 in, the top would be 1, and then the bottom would be negative 1. So you actually get negative 1. Okay. If I substitute in 6, I get 2 divided by negative 2. So I get negative 1. Hopefully you get the gist of this. And we know those points. If I put in 3, I would get positive 1, because absolute value, divided by positive 1. So you get positive 1 at 3. And hopefully if you put in 2, on top we'll get positive 2, because of absolute value, divided by 2, which gives us 1. So in this case, our graph looks similar, definitely not the same though. So you actually have to know which way this graph is going to go, because your answers will be completely different. So I'm going to answer the two questions of the limit as x approaches and as x approaches 4 from the left, and the limit, and I'll do that, I guess, right here, the limit as x approaches 4 from the right. So in pink, the limit as x approaches 4 from the left ends up giving you positive 1. In blue, the limit as x approaches 4 from the right gives us negative 1. So same thing, we have a limit at x going to 4 of f of x not existing. But I wanted to show you the difference between the two. Let's see what I got next. We have some sine of x over x. So remember when we looked at a graph, and I'm actually going to pull up the graph. So we have the sine of x over x. What I did for you was actually bring a graph up on the screen. And the one thing we should realize is that there is definitely a hole right there, a removable discontinuity. And the reason we know that is from class, we played around with looking at the table. And you can really see, we know that the value at 0 would be undefined. But everywhere else, the value is defined. So it's definitely only a removable discontinuity. So just by looking at the graph, we know that the limit as x approaches 0 for this is 1. What I wanted you to understand is that based on the limit value, so this was to 0, if I change it now and go to negative infinity, if we look at the graph going towards negative infinity, that would be this left side. And I'll do that in orange. Going to the left side, we're really going to bounce up and down, but we're going to just bounce less and less. And the reason that we used in class was because the sine of x really only goes from negative 1 to 1, but we're going to divide by negative infinity. And dividing by negative infinity or positive infinity, as long as the value on top is small, we're really going to approach a value of 0. And if you look at the graph, it would literally just bounce up and down, but lower and lower. And on the right side, as we go to positive infinity in purple, we're going to do the same thing. We're going to bounce, but just bounce lower and lower and lower. And so you'll notice that for the same reason, because sine of x over x, negative 1 to 1 is what sine of x does. Whatever value you substitute in for x, you're only going to receive range values from negative 1 to 1. And the denominator, you're really substituting in positive infinity. So take a number, divide it by a huge number, we're really going to go to a limit value of 0. So you can see that defining the c value here is what changes the answer, because it will be looking at different parts of the graph. And so when you look at number 4, I put these up so that you could take a look. Really, we're substituting in some values that get substituted in here, but since sine is taking on whatever this portion becomes, you're really still going to have an output value of negative 1 to 1. I know it looks horrible, e to the x squared plus pi, but your output value is still only negative 1 to 1. And then we're going to divide by positive infinity. That looks just like the problem from before, so that limit value is still 0. These over here to the right, number 5, were problems that you're really looking for the fact that the sine of x over x, the limit as x goes to 0, will give us 0. So I know that I need a 4x on the bottom, so I'm going to multiply the numerator and denominator by 4x. I'm going to rearrange my problem so that you see it better. I'm going to have the sine of 4x divided by 4x, and then multiply by the limit as x goes to 0 of the leftover numerator 4x and the leftover, which is cosine of x in the denominator. We know that the first portion here, the limit value is 1. That's a rule that essentially you've come to memorize. And the second portion here, we're really going to do 4 times 0 divided by the cosine of 0, which gives us 1 times 1. So the limit value of this one happens to be 1. So that's a type of problem where you're really attempting to get a sine of something over that same something. Okay? And I believe that was the last problem that I had for you. Hope this helped in reviewing for limits.